and welcome to today's lesson, where we will be talking about how to determine the critical points of a function, such as getting the local max, the local min, the POIs, and how we're going to use all of that through derivatives. So stay tuned to learn more. What the maximum point or minimum point of this particular function is, we're going to get the derivative. So the derivative of this we know will be 5x to the power of 4 plus 3x to the power of 2 based on the power rule that we learned before. And after, we need to figure out, well, what are the x values? So I'm going to factor this out. And when I do factor this out, I could take x to the power of 2 in common, and I am left with 5x squared plus 3. Over here, now I have an x value, which is going to be 0. And I have another x value, which does not exist. The reason why this particular one doesn't exist is because if I had 5x squared plus 3 equals to 0, that's 5x squared equals negative 3, x squared equals negative 3 over 5, x is equal to root negative 3 over 5. And we know that we cannot root any negatives. So based on that, we are now able to make our interval chart. And for our interval chart, we are going to have negative infinity. We are also going to have 0. And lastly, we are going to have positive infinity. For this part here, I have x squared, 5x squared plus 3, and f prime x. And I got all of that based on the factor that I got there. Next thing that I'm going to do is pick a testing point. For the testing point for the interval negative infinity to 0, I'm going to pick negative 10. And for the testing point for 0 to positive infinity, I'm going to pick positive 10. And if I plug in negative 10 into x squared, I will get a positive. And if I plug in negative 10 into 5x squared plus 3, I will also get a positive. So this over here, my result will be positive. And after, if I plug in 10 into the equation, I get positive here, positive here, positive here. Now, if we go back to our rules that we learned prior, which talks about local maximums are when we have the rate of change going from negative to positive, and local max is when we have the rate of change going from positive to negative. Over here, it's positive to positive. So pretty much what that means is that there is no local max or local min. And how this particular function would look like, if I were to sketch it out, was super small. Give me one sec. So if I were to sketch it out, here is the x and y intercept. That's positive, so it would go here, and then it would go here. So as you could see, there is no local max or min, because in order for it to be a local max, it needs to look like this, and in order for it to be a local min, it needs to look like that. And for this particular function, there isn't exact same steps that we did prior, where we have to calculate the derivative first. And we will be using the power rule again. If anyone has any question as to why I got what I did, please refer back to the power rule functions. Now that I have got the derivative, next step once again is to solve for the x-intercept. And what I'm going to do is factor this out, and I am able to factor out 4x. That gives me x squared minus 6x plus 9. And I'm able to factor the inner part as well by using the difference of squares. Sorry, not difference of square, perfect square, which is x minus 3 whole square. And now I have that one of my zeros is at 0. Another one of my zeros is at 3. And just like before, we're going to make our interval chart, but this time around we're going to have more points because there are more x-intercepts. So we have negative infinity, we have 0, and we have positive 3, positive infinity. I'm going to put 4x here, x minus 3 square here, and lastly f prime x over here. I'm going to do the exact same thing in between negative infinity and 0. I'm going to find a testing point. I'm going to say -1. In between 0 and 3, I'm going to find a testing point, which I'll say 1. And in between 3 and positive infinity, I'm going to find a testing point, let's say 10. So if I plug in -1 for the first one, that gives me a negative answer. For the second one, because it's being squared, it will give me a positive answer. So this over here is a negative. Plug in 1 into all of them. This is positive, this is positive, so that's positive. Plug in 10 into all of them. That's positive, positive, positive. Okay, now we have something. So as you could see, it goes from negative to positive. So our slope is going this way. Then it is going this way. So if it goes from negative to positive, that means this point over here will be a local min. And for the next one, it goes from positive to positive. And as we learned from our previous example, if the signs are the same, it is neither a local max or local min. So the 3 really isn't anything. So how our graph for this will look is, let's say this is where 0 is, this is where 3 is. That is positive, so it's going to come in from this way. How do I know it comes in from this way? Is because in advanced functions, we learned that if the degree is even and the leading coefficient is positive, it goes from quadrant 2 to quadrant 1. Bear with me. I'm not able to graph this properly. Okay, so it'd go like this, and when it hits 3, let's say at this point, it's going to make a POI. This way, this way. So our graph would look something like this. So notice this point is a POI and not a max or a min.